April 12, 1938, Union Pacific's test facility outside Omaha, Nebraska. The engineering report from visiting railroad executives would never fully capture what they witnessed that morning as General Electric's prototype gas turbine locomotive roared to life with a sound that defied everything steam power technology said was necessary for hauling freight. Through the diesel smoke and grinding steel of the test track, a single turbine unit produced horsepower ratings that seemed impossible to steam locomotive engineers. No massive firebox consuming tons of coal per hour. No complex valve timing mechanisms requiring constant maintenance. No boiler pressure limitations that restricted power output. Yet the prototype generated thrust that traditional steam power could not match. In conventional railroading, steam locomotives required extensive infrastructure to maintain operational status. Water towers every 50 miles, coal yards at major terminals, roundhouses staffed with skilled mechanics who understood the intricate steam systems. Each requirement added costs and operational complexity that consumed railroad profits. The turbines promised to eliminate these limitations entirely. Continuous power delivery, minimal mechanical complexity, fuel efficiency that transformed operational economics, power-to-weight ratios that made heavy freight movement possible with fewer locomotives. 800 miles from traditional steam facilities, the most decisive propulsion revolution in railroad history was revealing itself, not in superior engineering refinement, but in the raw power that eliminated steam's fundamental limitations. Union Pacific's chief mechanical engineer William Jeffers stepped onto the observation platform at the railroad's Omaha headquarters on May 15, 1938, carrying technical specifications for locomotive power requirements that stretched far beyond what conventional steam technology could deliver. Beside him, General Electric's turbine division chief Arnold McNeil hefted their shared prototype documentation, its weight representing everything they had developed from aviation turbine research. The two organizations had pooled resources, over $4 million between them, to develop gas turbine propulsion for railroad applications in a transportation network that promised unlimited freight demand and proximity to the expanding oil infrastructure that connected America's growing petroleum industry. Within months, they had finalized contracts for experimental turbine locomotives, their specifications promising performance that traditional steam power could never achieve. Union Pacific's expanding freight operations, fueled by wartime manufacturing demands and emerging interstate commerce, seemed to offer unlimited opportunity for high-horsepower locomotives. Yet as May turned to June, both organizations encountered the same problem, plaguing every transportation innovation from locomotives to aircraft. Theoretical power meant nothing without mechanical reliability. The mathematics were brutally compelling. Gas turbines could generate 8,000 horsepower from a single unit compared to the 4,000 maximum from the largest steam locomotives. Fuel costs would drop 70% compared to coal consumption. Maintenance intervals could extend from weeks to months as simple turbine mechanics replaced complex steam valve systems. The promise seemed irresistible, yet no railroad had ever operated turbine propulsion at the scale Union Pacific was proposing. The technology that powered aircraft might not survive the continuous operation, extreme temperatures, and mechanical stresses that railroad service demanded. Heinrich Müller, master locomotive engineer at Deutsche Reichsbahn's Munich workshops, demonstrated European conservative engineering standards during General Electric's research tour in 1937. Traditional steam locomotive development emphasized incremental improvements to proven technology rather than revolutionary propulsion systems. Boiler design refinements consumed decades of German engineering expertise. Valve timing optimization required generations of practical experience. Metallurgy improvements for high-pressure steam systems progressed through careful testing and conservative implementation. Each advancement built upon centuries of accumulated knowledge that European railroads considered irreplaceable. British locomotive manufacturers like Gresley and Stanier achieved remarkable steam efficiency through meticulous attention to thermodynamic principles. Their designs optimized every aspect of steam generation, distribution, and exhaust. Four-cylinder compound configurations extracted maximum work from each pound of coal. Streamlined casings reduced air resistance at high speeds. Precision manufacturing ensured reliable operation across millions of revenue miles. European railroads accepted steam's inherent limitations as fundamental constraints that defined railroad operations. Water requirements dictated route planning. Coal quality affected performance predictably. Maintenance schedules reflected the reality that steam locomotives were complex machines requiring skilled attention. American railroads faced different economic pressures that made European conservatism untenable. Union Pacific's transcontinental routes stretched across territories where water was scarce and coal deposits were distant from main lines. Operating costs per ton-mile determined competitive advantage in freight markets where trucking companies offered increasing competition. William Jeffers calculated that Union Pacific spent more on locomotive fuel and maintenance than on track infrastructure. Steam locomotives consumed 17 pounds of coal per mile, while requiring water stops every 100 miles. Maintenance facilities employed thousands of skilled workers whose wages made railroad operations increasingly expensive compared to highway freight alternatives. General Electric's turbine research offered a third option that railroad industry experts considered dangerously experimental: eliminate steam entirely through aviation-derived turbine technology. Their experience developing turbines for military aircraft and naval vessels suggested that reliable, high-power turbines were achievable if properly engineered. Yet aviation turbines operated intermittently under controlled conditions with extensive maintenance between flights. Railroad service demanded continuous operation across thousands of miles in extreme temperatures, heavy vibration, and contaminated fuel conditions. The operational environment was fundamentally different from anything turbine technology had proven successful in handling. Industry publications dismissed railroad turbines as theoretically interesting but practically impossible. Railway Age published editorials arguing that steam's proven reliability would always exceed experimental turbine systems in real-world service. No amount of theoretical horsepower mattered if locomotives could not complete revenue runs without catastrophic failures. As contracts were signed throughout 1938, Union Pacific and General Electric realized the challenge was larger than anyone had imagined. The Burlington Railroad's diesel-electric success had proven that alternatives to steam were commercially viable, but turbines represented a far more radical departure from conventional railroad propulsion. Their first prototype attempts would either revolutionize American railroading or prove that some technologies were too ambitious for practical transportation service. General Electric's prototype turbine locomotive arrived at Union Pacific's Omaha facility in January 1949, 11 years after initial development began. World War II had delayed commercial application, but military turbine research had advanced the technology dramatically. The prototype represented America's most sophisticated locomotive ever constructed. The initial trials appeared successful. GE's gas turbine unit produced 8,500 horsepower, double the output of the railroad's most powerful steam locomotives. Fuel consumption was 40% lower than comparable steam power. Mechanical complexity was reduced to levels that suggested maintenance would be minimal. Union Pacific's test engineers ran the prototype through standard acceptance procedures during February and March. Acceleration performance exceeded specifications. Tractive effort surpassed steam locomotive capabilities across all speed ranges. The turbine's smooth power delivery eliminated the wheel slip problems that plagued high-powered steam designs. William Jeffers authorized production of 25 turbine locomotives based on prototype performance, believing that GE's aviation-derived technology would transform Union Pacific's freight operations. The railroad's board approved $15 million for the turbine fleet, expecting rapid returns through reduced operating costs. The catastrophe emerged gradually during the first revenue service runs in June 1949 as Union Pacific deployed turbines on heavy freight routes across Wyoming and Nebraska. Locomotives that had performed flawlessly during controlled testing began experiencing failures that seemed to worsen with each 1,000 miles of operation. Turbine blade erosion from desert sand created vibration that propagated throughout the entire propulsion system. Bearing temperatures exceeded design limits during sustained high-power operation across mountain grades. Fuel contamination from the low-quality bunker oil Union Pacific purchased to reduce costs caused combustion chamber deposits that reduced power output dramatically. By August, Union Pacific had experienced its first catastrophic turbine failure when locomotive number 1003 suffered complete turbine disintegration near Rawlins, Wyoming. The turbine's rotor, spinning at 16,000 revolutions per minute, fractured from metal fatigue. Fragments penetrated the housing and destroyed the electrical generator before the emergency shutdown system could respond. The explosion sent turbine components through the locomotive's bodywork and ignited fuel lines, creating an intense fire that consumed the entire unit before fire crews could respond. The locomotive was destroyed completely. Only the quick response of the engineer and firemen prevented fatalities as they abandoned the machine seconds before the turbine section exploded. Union Pacific's engineering department initiated immediate investigations. Metallurgical analysis revealed that turbine blades were experiencing erosion patterns that had never appeared during controlled testing. The combination of sustained high temperatures, contaminated fuel, and abrasive particulates created operating conditions that aviation turbines never encountered. General Electric's designers had optimized turbines for clean jet fuel and intermittent operation. Railroad service demanded continuous power output using the cheapest possible fuel in environments contaminated with dust, sand, and industrial pollutants. The operational reality was destroying turbines faster than anyone had predicted. Despite the Rawlins explosion, Union Pacific continued turbine deployment throughout 1950 and 1951. The locomotive's extraordinary power output made them irreplaceable for heavy freight service across the railroad's most demanding routes. No other locomotive type could match their performance when they were operating properly. Union Pacific's operational data revealed the turbine's remarkable capabilities during successful runs. A single turbine could haul freight trains exceeding 6,000 tons across Sherman Hill's steep grades without helper locomotives. Multiple turbine units working together moved trains approaching 10,000 tons, loads that would have required 5 or 6 steam locomotives. The turbines transformed Union Pacific's competitive position in transcontinental freight markets. Transit times decreased 20% compared to steam-powered operations. Fuel costs dropped as predicted despite using cheaper grades of oil. When turbines completed runs without mechanical failures, their economic advantages were undeniable. Yet reliability remained catastrophically poor. Turbine availability averaged only 65% during 1951, meaning that 1/3 of the fleet was out of service at any given time. Maintenance costs exceeded projections by 200% as mechanics struggled to repair systems that had never been designed for railroad operating conditions. The technical problems multiplied as operating experience accumulated. Turbine inlet temperatures reached levels that caused progressive metallurgical degradation. GE had designed blades for 1,200 degrees Fahrenheit, but railroad service generated sustained temperatures exceeding 1,300 degrees during heavy tonnage operations. Combustion chamber linings deteriorated from thermal cycling as locomotives alternated between full power and idle. Aviation turbines operated at relatively constant power settings. Railroad service demanded frequent power changes that created thermal stresses the combustion chambers could not withstand over extended service intervals. Bearing failures became epidemic as lubricating oil contaminated with combustion residues lost its protective properties. High-speed turbine bearings required extremely clean oil to prevent premature wear. Railroad operating environments made maintaining oil cleanliness nearly impossible despite elaborate filtration systems. Union Pacific's maintenance facilities developed specialized procedures for turbine overhaul. Complete turbine section replacement every 90,000 miles. Combustion chamber inspection every 30,000 miles. Bearing replacement every 60,000 miles. The intervals were far shorter than GE's original specifications had predicted. The railroad's Wyoming division experienced particularly severe turbine problems. Desert sand drawn into turbine intakes caused blade erosion that reduced power output within weeks of major overhauls. Engineers reported power losses exceeding 20% between maintenance intervals as eroded blades could no longer extract energy efficiently from combustion gases. Temperature extremes across Union Pacific's operating territory created additional challenges. Winter cold caused fuel flow problems that aviation turbines never encountered. Summer heat pushed cooling systems beyond their design capacity. The turbines that worked adequately in moderate climates failed consistently at temperature extremes. By 1952, Union Pacific's engineering staff recognized that first-generation turbines represented an expensive experiment in railroad propulsion. The locomotives produced extraordinary power when operating, but their mechanical unreliability made them economically questionable despite their theoretical advantages over steam power. The explosion that nearly destroyed Union Pacific's reputation occurred on November 3, 1952, when turbine locomotive number 1017 suffered catastrophic failure while hauling a priority freight train through Echo Canyon, Utah. The incident revealed fundamental design flaws that no amount of maintenance could address. The locomotive had completed a major turbine overhaul just 2 weeks earlier at the railroad's Cheyenne shops. All components had been inspected and replaced according to General Electric's specifications. The turbine section had been balanced dynamically to eliminate vibration. Combustion chamber linings were new. Bearings showed no wear during final inspection. Yet as the locomotive accelerated through Echo Canyon under full power, the turbine's rotor assembly began vibrating at frequencies that exceeded all design parameters. The vibration propagated through the mounting structure and into the locomotive frame. Within seconds, the turbine's containment housing fractured. Turbine fragments, each piece weighing several pounds and traveling at supersonic velocities, penetrated the locomotive's fuel tanks. Bunker oil ignited instantly, creating an intense fire that engulfed the entire power unit. The explosion was visible for miles as burning fuel created a fireball that rose hundreds of feet above the canyon floor. The train's engineer, Robert Morrison, managed to separate the burning turbine unit from the freight cars before abandoning the locomotive. His quick thinking prevented the fire from spreading to cargo that included flammable chemicals and petroleum products. The locomotive burned for 6 hours before fire crews could extinguish the blaze. Investigators from Union Pacific and General Electric spent weeks examining the wreckage. Metallurgical analysis revealed that the turbine rotor had developed microscopic cracks from thermal fatigue. The cracks had propagated until the rotor's structural integrity failed completely under the centrifugal forces generated by 16,000 RPM rotation. The Echo Canyon explosion forced Union Pacific's board to confront uncomfortable truths about turbine technology. The railroad had invested over $20 million in locomotives that were destroying themselves faster than maintenance could prevent. Insurance costs were escalating as underwriters recognized that turbines represented catastrophic fire risks. Industry publications seized on the failure as proof that gas turbines were unsuitable for railroad service. Railway Age published detailed analysis showing that turbine operating costs exceeded diesel-electric alternatives by 40%, when all maintenance and reliability factors were included. The theoretical fuel savings were being consumed by mechanical failures and extensive overhaul requirements. Other railroads that had considered turbine purchases canceled their orders. Southern Pacific, which had planned to acquire turbines for their California routes, shifted entirely to diesel-electric power. Santa Fe Railroad's chief mechanical officer publicly stated that turbines were too experimental for commercial railroad operations. Union Pacific faced a decision that would determine the railroad's future: continue operating turbines despite their catastrophic failure rates, or abandon the technology entirely and accept the financial losses from locomotives that had failed to deliver their promised revolution. Rather than abandoning turbines completely, Union Pacific partnered with General Electric to develop second-generation designs that addressed the catastrophic failures plaguing first-generation units. The new turbines, designated veranda models for their distinctive external walkways, entered service in 1954 with modifications that engineers believed would eliminate the mechanical problems. GE's redesign focused on the fundamental issues revealed by 3 years of operational failures. Turbine blade metallurgy improved through cobalt-chromium alloys that resisted erosion better than earlier materials. Combustion chamber linings incorporated ceramic thermal barriers that withstood temperature cycling. Bearing systems used improved lubricants and elaborate filtration to prevent contamination damage. The veranda turbines produced 10,000 horsepower, making them the most powerful land vehicles ever constructed. Union Pacific deployed them on the railroad's heaviest freight routes, where their enormous power output provided advantages that diesel-electric locomotives could not match. A single veranda turbine could replace 3 diesel units on mountain-grade service. Initial operational results appeared promising. Turbine availability improved to 75% during the first year of service. Major component failures decreased as improved materials withstood railroad operating conditions better than first-generation designs. Union Pacific ordered additional units, believing that the technology had finally matured into reliable service. Yet, the fundamental economic problems remained unsolved. Fuel consumption, while better than steam locomotives, exceeded diesel-electric efficiency by 30%. The turbines required expensive bunker oil while diesels could operate on cheaper grades. Maintenance costs stayed elevated despite reliability improvements, as turbine overhauls demanded specialized facilities and expensive components. By 1958, changing railroad economics made turbine operations increasingly questionable. Diesel-electric technology had evolved rapidly, with manufacturers like EMD and Alco producing reliable locomotives that matched turbine power output through multiple unit configurations. 4 diesel units provided the same horsepower as a single turbine, while offering redundancy that turbines could not match. Union Pacific's financial analysis revealed the decisive factors. Diesel-electric locomotives operated 42,000 miles between major overhauls. Turbines required heavy maintenance every 30,000 miles. Diesel parts were standardized across the industry. Turbine components were custom manufactured at premium prices. Diesel mechanics were available throughout the railroad network. Turbine specialists required extensive training and commanded premium wages. The railroad's last turbine orders were placed in 1961. Not because the technology had failed completely, but because diesel-electric alternatives had become economically superior across every operational metric. Union Pacific continued operating turbines through the 1960s as their enormous power remained useful for specific heavy freight applications. The final turbine locomotives were retired in 1969, ending 30 years of experimental railroad propulsion. The machines that had promised to revolutionize American freight transportation had proven too expensive, too complex, and too unreliable to compete against simpler diesel-electric technology that had evolved into the industry standard. Union Pacific's turbine experiment left a complex legacy that influenced American railroad engineering for decades after the last turbine was retired. The locomotives had demonstrated that revolutionary power output was achievable, but they had also proven that raw horsepower meant nothing without economic viability and mechanical reliability. The turbine's most significant contribution was accelerating diesel-electric development through competitive pressure. General Motors' electromotive division responded to turbine power ratings by developing higher horsepower diesel units that eventually matched turbine capabilities. The SD45 and DDA40X diesel locomotives produced power outputs that would have seemed impossible without turbine competition. Multiple unit diesel configurations, where several locomotives operated together under single control, emerged partly as a response to turbine power concentration. Railroads discovered that distributing power across multiple diesel units provided operational flexibility that single high-powered turbines could not match. A diesel car could lose 1 unit and continue operating. A single turbine failure stopped the entire locomotive. The turbines influenced modern railroad engineering through lessons learned from their failures. Maintenance accessibility became a critical design parameter for subsequent locomotive generations. Standardization of components reduced operating costs across the industry. Fuel efficiency emerged as equally important as raw power output. Several turbines survived into preservation as museums recognized their historical significance. The Illinois Railway Museum preserved one of Union Pacific's veranda turbines, maintaining it as a monument to experimental railroad technology. The Union Pacific Railroad Museum in Council Bluffs displays turbine components and documentation showing the development process. Railroad historians debate whether the turbine program was a costly failure or valuable experiment. Union Pacific invested over $50 million across 30 years with limited commercial success. Yet the knowledge gained influenced subsequent locomotive development and demonstrated that American railroads were willing to pursue revolutionary technologies despite significant risks. The turbines represented the last major alternative to diesel-electric propulsion that American railroads attempted at scale. No subsequent technology, not coal turbines, not nuclear power, not modern gas turbines, ever matched Union Pacific's commitment to developing fundamentally different railroad propulsion systems. Modern railroad engineers studying the turbine program identify specific technical decisions that doomed the project. Using aviation-derived turbines without sufficient modification for railroad service, accepting cheap bunker fuel that destroyed turbine components, underestimating maintenance requirements. Each mistake offered lessons that influenced subsequent engineering decisions. The turbine's ultimate legacy was proving that railroad propulsion technology required optimization for specific operating conditions rather than raw performance maximums. Diesel-electric locomotives succeeded because they balanced power output, fuel efficiency, maintenance requirements, and operational flexibility into systems that worked reliably across millions of revenue miles. Union Pacific's turbine experiment showed that even groundbreaking power came with costs no railroad was ready to pay. The machines that once promised the future became cautionary tales demonstrating that revolutionary technology requires more than engineering brilliance. It demands economic viability, mechanical reliability, and operational practicality that turbines never achieved.